we want to evaluate the integral over that curve C of x squared dx plus y squared dy plus z squared dz on the line that goes from 1 to -1 to 3 to 0. Okay. You're going to start out in a very similar way to what we did in the last example. You need to parameterize your curve. In this case, your curve is a line. So the line with beginning point 1, 2, -1 and ending point 3, 2, 0. This goes back to the very first chapter. How do you parameterize a line? You need two things. Anybody remember what they are? This is good review for the final. You need a direction vector, right? It kind of acts like slope does in the plane. You need a direction vector. And you need at least one point on the line. You've got 2 points. And then you use the parametric equations of the line. Remember, what do those say? X equals x naught plus at. Y equals y naught plus bt. And z equals z naught plus ct. Where your direction vector is the vector ABC. Does that look familiar? It's been a while, right? But these are the parametric equations of the line, and therefore they give you a parameterization of that line. Okay, how do we get a direction vector then? Let's call these points P and Q. So, yeah. The direction vector would be PQ. And we take the tip minus the tail. So what would that be? Just to show the details, because it's been a while, we would take, so the tip would be Q and the tail would be P, right? So we would take 3 minus what? 3 minus this 1. There's your first component. And then 2 minus 2, 0 is going to be your second component. And then 0 minus a -1. So 1 would be your third component. So what would that be? 2, 0, 1 is your direction vector. That's your direction vector. Does that look familiar to you? It's supposed to be a V there. Yeah? Okay. So let's come up with the parametric equations then. So you're basically filling in these guys, right? Let's use this point, 1, 2, -1. So then what does x become? For your now, so we're coming up with the parametric equations using this first point as my x naught, y naught, z naught. What do you get for your parametric? What does x equal? X equals 1 plus 2t, right? And y equals 2 plus 0t, right? So just 2. And z equals -1 plus t. Does everybody buy that? Now, you do, for all of these problems, you're going to need the limits on t, because those give you the limits of integration. So what is t going to range from? To produce this first point P, t could be what? If you think about it, if you look at your parametric equations, to produce coordinates 1, 2, -1, well, from these parametric equations, what would t have to be? 0. Yeah, you plug in 0 here, you get the 1. It doesn't matter what you plug in here, you get 2. You plug in 0 here, and you do get the -1. And then, what's the upper limit on t to produce q? 3, 2, 0. 1. You can see that if you plug in 1 for t, you get 3, 2, 0. Okay? Everybody believe that? Except there's a problem with this one. Why isn't it working there? Yeah, we must have made a mistake on it. Huh. That's why you should always check it to make sure you get your beginning point and your final point. So let's double check it. Z naught would have been what? That would be -1. And then it's this guy, the C, that should have just been 1, right? And somehow I plugged in 2. But that's why you check, and you can find those mistakes. So it should have been -1 plus t. Yeah. And now it works, right? When you plug in t equals 1, you do get just a 0 here, which is what you're supposed to get for the final coordinate in Q, the ending point. So it's going to work. Okay. Mistakes happen, but if you know what you're doing, you can find them. So in terms of R of t, not that we need it here, we're not going to use R of t, but if you wanted to write in terms of R of t, what would the line be in terms of R of t? It would be 1 plus 2t, comma 2, comma -1 plus t. But when we're in differential form, we're not. I'm going to erase this because we're not actually going to use R of t. I want to make sure you're making those connections. Okay? So we actually don't need R here, R of t. I just want to make sure you recognize what R of t would be if you use the other formula. Okay, so if you think about it, go back. It's differential form is, once you understand what it's saying, is almost easier to use than the other equation. Because differential form tells you everything you need. You need to get everything in terms of one parameter just like before. And the differential form tells you need dx, you need dy, you need dz. And you need to get x and all the differentials, dx, dy, dz, in terms of t, if that's your parameter. And by leaving the parameterization in terms of the parametric equations, we can do that easily. So we've got x, y, and z in terms of t from the parametric equations automatically. And then we can get, just by looking at these, we can get dx by taking the differential of the first parametric equation. What do you get? What's the derivative of 1 plus 2t with respect to t? 2, and then, since it's a differential, it's 2 dt, right? What's the derivative of y with respect to t? So dy is going to be 0 dt, right? Because 2 is a constant. So just 0. And then what's the derivative of z with respect to t? Just 1. So what's dz then? dz is 1 dt. So we've got everything we need then to plug in to the differential form in terms of t. Okay, so let me copy this guy so you can really see it in action. It's kind of a neat notation, it really is. So when I plug in here, let me erase this errant mark. Okay, so now let's plug in. Now you can see what I'm doing. Okay, so x squared, so what am I plugging in for x squared? What am I plugging in for x, rather? 1 plus 2t, and then I'm going to square it, aren't I? And then what am I plugging in for y? Does it matter? No, because dy is 0. So this whole piece is going to 0 out. Don't even look at it. Then what am I plugging in for z? -1 plus t. And then for dz, dt, and then for dx, I think I forgot to say I got to plug in 2 dt. So you just make the substitution, you guys, and you've got yourself an integral with respect to t. Check it out. You get the integral of, 1 plus 2t, that's quantity squared, that's the x squared part of it, and then don't forget the dx, which includes an extra factor of 2, so 2 dt. There's your x squared dx, plus, z is -1 plus t, we're squaring that, and then dz is just dt. And then look, and then what are the limits of integration, by the way? 0 to 1. But then look, if you just factor out the dt, it really is a calculus 1 type integral, isn't it? So you get the integral from 0 to 1, 1 plus 2t quantity squared times 2 plus negative 1 plus t quantity squared, and then I'll put brackets around that entire thing, dt. So I kind of like that notation because it's a more natural transformation going from, you know, in terms of x, y, and z to in terms of just a single parameter t. So what would we have to do to evaluate this thing? Oh, I guess we got to do some multiplying, don't we? What's 1 plus 2t quantity squared? 1 plus 4t plus 4t squared, and then we got to multiply that whole thing times 2, and then what's negative 1 plus t quantity squared? 1 minus 2t plus t squared, right? No parentheses needed because we're not multiplying that times anything. Close bracket dt. And then this part just becomes everything inside doubled, right? So 2 plus 8t plus 8t squared. So let's add like terms then between the stuff in pink and the rest of the stuff in green over here. So what do we get? Integral 0 to 1. Let's go in descending powers. What would we get? 9t squared. And then what would the coefficient of t be? 6, so plus 6. And then the constant would be 3 dt. And then you get a reasonably easy integral when all is said and done. Integrate, what do you get? 3t cubed plus 3t squared plus 3t. Gosh, you haven't seen one this easy in a long time, have you? So the lower limit's not going to affect anything. It's going to zero out. So it's just 3 plus 3 plus 3. I think that's 9. There we go.